Hey folks, tonight I've got another job on the Bridgeport here with a rotary table. I'm going to be resurfacing this 17-inch diameter drum. This is a brake drum from a Caterpillar road grader. It is approximately 4.5 inches deep and 17 inches in diameter on the wear surface. And the reason why I'm machining this is that somebody ran the brakes to bare metal and it badly damaged the surface. I'll bring you in for a close-up in a little bit, but there is about 60 or 70 thousandths deep grooves in the surface, and there's also wear from the life of this machine. So what my plan of attack is I've got the drum mounted on this rotary table with a subplate, and I've got a 2-inch diameter end mill in an end mill holder in the Bridgeport, and I'm going to bring this through and I'm going to use the rotary table to mill the inside surface of this. I chose to do this on the rotary table because the back plate I have for my lathe is not correct. That lathe was made in 1985 and they managed to machine the taper incorrectly when they made the back plate. So until I fix that or get another one, I really can't stick stuff this big on there. The other thing is I'd have to pull the gap out of my lathe in order to fit this, and I haven't pulled the gap before, so it's a little bit of a challenge, but it could also be a giant pain. And so I wanted to see if this method worked, and I did some test cuts last night and this will work, so I'll bring you along for the ride. I'm going to bring you up close and show you the setup and give you some details, try to answer those questions before people ask them. If you've seen my video on machining the rotors for my Volvo, then you're probably familiar with what I'm about to do, but it's a little bit different, and based on the feedback on that video, I'll give you some details about this before I actually start doing the machining and publish the video. Okay, so what you see here is this 2-inch diameter by probably 2 3/8 or 2.5 inch length of cut. It's in an end mill holder because I need the reduced shank here to be able to step down the 4.5 inches. So I'm going to be taking this in passes, kind of how you see here, and then I'll step down, take another pass. So the previous pass will create clearance for the next pass. Now, the way I mounted this up is I have this sheet of aluminum or plate. It's 5/8 inch thick, 60/61. This is an 18-inch square plate. I drilled the bolt circle to mount it down to the rotary table, and then I eyeballed it to the center, and then I bored a hole in there so that I could stick a Morse taper adapter and small chuck adapter in there so I could dial in the center of the rotary table while the plate is on here. So the plate is centered more or less on the rotary table, and then I used the inside diameter here of the drum to sweep that to get it centered up. So this is centered and the drum is centered, so it's going to spin on the axis. And then once I got it centered, I zeroed out my DRO so that I could preserve my machine datum. So let me bring you underneath to see some of the challenges here. Now, in their infinite wisdom, whoever designed this made the handle bigger than the clearance to the table, and because of that, I had to use some 1, 2, 3 blocks as spacers. So those are underneath here. The plate is clamped down with some long bolts to the 1, 2, 3 blocks, and then the drum is clamped down to the subplate using 1/2-13 bolts. There's only 4 of them, even though there's 8 holes. These are, I believe, 9/16 20 or 5/8 18 bolts. But anyway, this is, if I can get a good picture here, hopefully you'll be able to see the damage. So you can see there's quite a bit of grooving there. And you can really see it in the relief in these cuts right here, just how deep it is. I haven't decided if I'm going to cut that to the full depth where it's a complete cleanup, or if I'm just going to try to get the high spots and maybe leave a couple low spots. To give you a sort of a scale or scope of things, this drum measures 17 inches from here to here, and this is 4.5 inches deep. The size of the brakes on this and the amount of wear they're going to experience in, you know, a 15-mile-an-hour vehicle is not extreme. There's not going to be a lot of vibration due to an imperfect surface finish. And on top of that, locating this center to the axis, if I get it within 5 thousandths, that's 1/3400th of the diameter of this. So that's a pretty small tolerance, pretty tight tolerance for such a large piece. So let me get the camera set up and I will give you a good view of this and we'll get started. Okay, we're gonna try this. I'm not really liking how much this end mill is running out here. The end mill holder, I think, probably isn't that great. Last night I made a test cut with a taller end mill held in a collet, and that seemed to have very little run out, so we may switch up to the long end mill, just running in the collet and the spindle, and then whenever I get down to that bottom I might have to get a little tricky. But what we're going to do is we're going to try climb cutting this. I'm running 200 RPM, low range, and I've got the table locked in here. I just kind of touched off on my previous cut, and we've got the X and Y locked. And you can hear how irregular that is. Okay. You might ask, why am I doing a climb cut instead of conventional? Well, when I tested this out, I found that it shattered less when I do a climb cut. And since this is a worm drive, there is very little chance or danger in doing a climb cut because it's not going to spool or take up lash, or it's already biased. The worm is very snug. I'm curious how this would work with that other end mill and the collet, so I'm going to pause this and swap end mills and then try it out. Okay, we're back. I swapped out that tool holder because it had somewhere in the neighborhood of 3 to 5 thousandths of run out. I've got this, this is a 1.866 regrind. The other one was a 2-inch, so they're fairly close in size. I've just touched off a little bit, and we will come up and then do a test cut with it. Having that end mill hanging out might be ill-advised. evidently that bolt stuck up a little more. That one had the thick washer, that's why. It's weird because I made a previous pass with that. Okay, well, we're gonna have to shut it down and gonna have to re-zero everything. It doesn't look like there's anything that's been harmed. I don't think the end mill's damaged. The end mill looks like it's running through. So I gotta re-zero everything, which is gonna take me a little while. So anyway, this is good for now. I'll be back on it in a minute.
Round 2. Fight!
Well, it's round 2. After the little mishap I got on camera there, I re-zeroed the rotary table. So I put a Morse taper down in there, specifically this one. Eyeballed it with a center and then dialed in that taper. So the rotary table's centered up again. And then after that, I double checked the inside diameter of the mounting surface on this drum, because this is a locating surface for the drum on the wheel assembly. So I got this zeroed back up. It's within about 0.03 of concentric to the rotary table. And I've switched up to this 1-inch diameter, 4-inch length of cut end mill. It's a 6 flute. It sticks out almost about 4.5 inches, so it'll get me to full depth here. Originally, this is what I started with, but I switched away from it, I think because it was a little bit off center, and I thought maybe the 2-inch or the 1.86 diameter end mill would work a little better. The reason why I'm switching back to this is that the current theory or accepted practice in machining is what's called high-speed machining. The underlying principle of high-speed machining is full axial engagement, which is the full depth of cut of the end mill, but a very small radial engagement. And the radial engagement is measured in degrees. So if you have a specific depth of cut that you want to make, a larger diameter end mill for the same depth of cut is going to have, it'll have a smaller number of degrees because it's larger, but you'll have more engagement surface, more circumference of the end mill actually engaging the part. And in an application like this where you don't have a lot of rigidity in your fixture or your milling spindle, a smaller circumferential engagement, I believe, is going to produce less chatter. That's the theory, at least. We'll see how well it works. So this end mill should get us done. The only roughing that I have left to do is down towards the bottom of the drum, and once I've finished that roughing, then I can start my finish pass. I think what I'll probably end up doing is blending the finish pass with each one of these bolt holes, because I have to remove each one of these bolts in order to machine that area. So it's going to be a bit of a game of hopscotch where I rotate it around. When I get to a bolt, take the bolt out, machine that area, put the bolt back in, go to the next bolt, take it out, machine that area, put it back in, and so on and so forth. So anyway, we're going to see how well this works. I am running the spindle at 400 RPM right now, or at least that's what it's set for. And I'm just feeling a little bit of slack up in the drive engagement here where the drive dogs are. Anyway, let's get to it. Yeah, I did ensure there's sufficient clearance. So we won't have another replay of yesterday's mishap. So I've got a quill stop here, I've got the DRO dialed in for that depth, and then we have sufficient clearance with the quill fully retracted, and we will have a 0 reading at the stop when we're at the full depth of cut. So let's go. So we're going to be climb cutting again. Wrong way. Okay, I've slowed it way down, and that seems to improve the surface finish, so we're going to go that way. Okay, for some reason my camera is complaining. I don't know why. My camera phone. So this is going to be a little tricky. Okay. So that groove measures about 21.8 thousandths. It's substantial, but like I said, you've got a bearing surface on the pad of about 4.5 inches wide, and these shoes are, ostensibly 17 inches in diameter. So a small groove like that isn't going to have much significance. So to answer a few questions before they pop up, the strategy I used to try to limit chatter, which was mostly successful, you either increase your feed or slow your speed, which effectively does the same thing. I didn't want to increase the feed because that would have, to a large part, it would have made the surface finish worse. What I did was slow the feed and slow the speed, so that way the marks, instead of being at an angle, because the flutes, as you go across in a climb cut, the flutes are going to leave an angled mark, sort of like a moire pattern on there. By slowing the spindle speed down by half and then maintaining about the slowest feed I could go, those marks are now vertical, so it's a bunch of vertical marks instead of horizontal marks. Those, I think, will bed out a lot better than the diagonal marks. So pretty much the rule is that in milling or lathe turning, to deal with chatter, you either increase your feed or you increase your depth of cut or you slow your speed down, because any one of those variables, if you change them, is going to change the parameters that are causing that harmonic to feed back, and you'll disrupt it. In this case, like I said, I just slowed the spindle speed down by half and kept the feed about the same, and that worked a lot better to improve the finish. I took a lot of spring passes on this just because there was a lot of spring in that end mill. It's a high-speed cobalt end mill, 1 inch with a 6, it's a 4-to-1 depth of diameter ratio, and high-speed steel or steel is generally like 3-to-1 at best. So we were on the hairy edge on that anyway. Couple other things. Why did I only make one pass around the bottom? Well, I had already made enough passes around the top that by the time I got to the bottom, the top of the end mill was actually kind of rubbing a little bit right here where there wasn't any flute. And so by coming down here, that flute where it was rubbing was actually kind of stabilizing in the existing cut, and there's no perceptible lip right here on that last cut because it was a fairly small cut. Why did I only use 4 bolts? Well, I didn't deem it necessary to use 8 bolts. Why didn't I put that last bolt in after I pulled it out? Well, I was finishing up the cut and it wasn't chattering or humming or anything like that, so instead of stopping and risking having a vertical line from a dwell, I just decided to keep going. What's a strategy for dealing with dwell in a situation like this? Well, I tried 2 methods. One was to stop the spindle and hit the brake at the same time as I stopped rotating this. That has variable effects. When you start it back up, ideally you want to kind of back off of where you want to go back to a spot you've already machined, start your spindle, then come in and then kind of pick up, and then you won't get dwell marks. On a CNC machine you could do that. On this I couldn't. Why didn't I use like a big giant boring head apparatus or some shop built thing to board out? Well, I didn't do that because experience tells me that no matter what I try, that would have just been a chatterfest and it would have been impossible. By using an end mill in here, I'm limiting the amount of contact and the amount of flex in all of the systems. So the knee flexes, the saddle rocks and flexes, the table flexes, the rotary table has some flex in it, this aluminum plate has flex in it. The fact that I've got it up off of 1-inch blocks here creates flex. These bolts have flex. To some degree this has some flex. Even though it's tapered, it's designed to help resist flex. The end mill certainly had a lot of flex. The holder and, you know, up in here inside the bearings, you know, created flex. If I had to guess, I would say that that end mill probably had somewhere in the neighborhood of, I don't know, at least half a thou of flex, because doing those, you know, spring passes, it kept cutting. And whenever I unlocked the table moved 2/10, and you could hear a change in the pitch, that it was cutting substantially more. So, you know, even 2/10 in the table move, and the end mill is cutting a significant amount. So there's a lot of flex and all that. It's done. It's going to be totally acceptable for the task at hand, and the machine will get put back on the road plowing snow. So thanks for watching. I know my last video like this got quite a few views and whatnot. If you like this video, give me a thumbs up, share it, you know, comment. I enjoy thoughtful comments. So thanks for watching. Bye.